in a polycrystalline state, or it can be grown epitaxially, which epitaxial is a Greek word which means having the same crystal structure as the substrate. So silicon itself can be deposited, and we'll talk about that in the next couple of lectures. So we're going to talk about the methods, the equipment, and some basic concepts used to deposit or grow these thin films. So let's just go back to a picture that I think I showed earlier in the course, but it's a cross-section view of, say, devices in a CMOS chip. And we've got our silicon substrate down here at the bottom. We've talked a lot about how to create N wells and P wells by ion implanting and diffusing and the source drains and all that. But there are a lot of other films here besides silicon substrate. So everything that's in a color other than white here is some other film. For example, here we might have copper that's used in the interconnect wiring, or aluminum, or tungsten. The shown here in this bright magenta. These hatched regions that are blue could be a low temperature oxide. Now it's a deposited oxide, very different from a grown oxide. So we're going to talk about how we deposit oxides by a process called chemical vapor deposition. Or it might not be oxide. It could be generally referred to as an interlayer dielectric in between some of the metal layers, and that has a low dielectric constant. And we'll talk about that in a little minute, why we want that. Other films that are absolutely critical for the MOSFET itself, we haven't talked about. We've been talking about polysilicon gates. So far, I just draw them in PowerPoint just by slapping them in there, but they don't get slapped in PowerPoint. They have to be deposited. So we'll talk a little bit about the deposition of polycrystalline silicon, which is critical. The deposition of the materials that are going to form the spacers, which is either this bright green silicon nitride, again, deposited, or it could be low temperature oxide. So there are a lot of different materials that we want to talk about and how they go down. Besides how they go down, there's some requirements or goals, if we go on to slide number 3, for thin film deposition. We need to be able to control the material composition. So either a stoichiometric SiO2, for example, or silicon 3N4 for silicon nitride, or it could be an oxynitride, a mixture of silicon, oxygen, and nitrogen. But we need to be able to have a process that reliably controls the atomic composition. We would like to have low contamination in general in order to control the electrical and optical properties of this material, and good electrical and mechanical and optical properties generally. An somewhat obvious thing, but very important, is we need to control the thickness uniformity across the wafer and from wafer to wafer, so that when we go to etch it or whatever, we know what the uniformity is, what the thickness is at any given point on the wafer. There's something called step coverage, which I'll give you an example in the next couple of slides of what we mean by step coverage. We often want conformal deposition, and we'll give illustrations of that. We want to be able to fill spaces in between lines. We don't want to have voids usually, and there is a need to planarize films. That is, create. We have a topography that often has a lot of hills and valleys. We often need to planarize it to give a smooth, flat top surface. It turns out that certain deposition techniques themselves tend to be self-planarizing, and we'll talk a little bit about that. So these are some requirements that people worry about when they're talking about coming up with a deposition procedure or process. Let's give some examples of these issues. Some of the ones that may be not so obvious here on slide number 4. What is step coverage? Okay, well, step coverage is when we have a step that exists. So let's say I already have this step here. You see this, there's maybe a material here, this metal line, and then we have a step going over it. It could be an oxide. And now I want to put a metal down. So I'm going to either evaporate it, or I'm going to sputter it, or somehow put the metal down. But you can see here I'm getting very uniform step coverage. Regardless of when I go over the step, I get the same thickness and conformality of the film. That's good. That's uniform step coverage. This is what's called poor step coverage. What does that mean? Well, right at the point of the step, you can see that the film thickness is, with respect to the surface here, is actually less. It's thinned down here. So that's poor step coverage. It's not conformal. And so the problem with this is is if your step coverage degrades at some point, this can be a weak spot in the metal line, and you could get an open. So step coverage is an important property of the type of deposition. So this would be considered poor step coverage. How about a filling issue? Okay. Well, what we mean by this is an example of metal that has been shows good filling into a via. So here I have a flat surface. I have a deposited oxide, and I've etched a hole, and I want to deposit the metal onto the surface and fill the hole. So that's good filling of the via. Here's an example where we had metal to start with, these two metal lines. They had a certain height and width and spacing, and we were trying to deposit oxide over them. And you notice we did not fill the space completely in between the two metal lines. We end up with a void. So that would be kind of a poor fill. We have voids. So we not only have to fill vias, where we've etched, this is a via where I've etched into a film, but we may have etched features that we're trying to cover up, and we want to fill the space in between them uniformly. And then here's an example of, the third example on the right is showing trying to etch, or rather fill a via where we have poor bottom filling. Here we get a nice metal film on top. The metal is not very well uniformly deposited on the edges, and the bottom doesn't fill very well at all. So there's an example of poor bottom filling. So this particular methodology, we'll talk about how this happened. This probably happened in some kind of evaporation or some type of line of sight type of deposition. So depending on how we do the deposition, we can get different quality of filling. Those were cartoons here on slide number 5. These are some actual micrographs. These are scanning electron micrographs taken in an SEM microscope. I took these directly out of your text. The one on the left, labeled A here, is an example of poor metal step coverage. This is a sandwich layer where titungsten was put down, aluminum, then aluminum, and then titungsten. So it's a tri-layer stack deposited by sputter deposition over an oxide step. So this is the oxide step here, right at this point. And you can see the tri-layer stack here. It's kind of hard to identify the different layers, but has this sort of thickness over here and a certain thickness over here, but it did not cover the step. And in PowerPoint, unfortunately, this didn't scan all that well, but you can see that the metal layer is thinned down where it goes over the step. On the right-hand side, these are a series of metal lines. Each one of these is a metal line going into the board, and oxide was deposited over these metal lines by chemical vapor deposition, and there were very narrow spaces between the lines. The spacing is less than a micron, maybe half micron. And you can see in the deposition of the oxide, when it gets the spacing gets to be quite narrow, as in the case between these two metal lines, you actually get voids. So the oxide did not fill in here. When the spacing was wider, as in this case, you didn't get the voiding. So when we get below a certain spacing, and this is a typical test structure one could use to figure out what's my critical spacing below which I start to get voids. And so again, this is a property, this voiding will be a strong function of the method by which the oxide is deposited. Okay, so those are some practical examples of issues with film deposition. Let's go on to slide number 6. There is an important concept when people are doing thin film, describing thin films, deposition, and that is called aspect ratio. We abbreviate that in this class AR. And the aspect ratio is just simply defined as the height of a feature. So if we have a metal line, it says height H divided by the width of the feature, W. So a metal line, it looks like this is the aspect ratio, H over W. For a contact hole, we also speak of an aspect ratio. It's the height or the depth of the hole divided by its width. Aspect ratio tells you something about the topography. In general, a high aspect ratio structure is more difficult to fabricate than a low aspect ratio one. For example, it's hard to make a very, very deep, imagine this being very deep and narrow contact hole. It has a high aspect ratio, say 2 to 1, and it's harder to etch it for one thing, and it's going to be harder to fill it. As you can imagine, as you go deeper and deeper down, it's going to be harder to access the bottom of the hole. So In one of the requirements people talk about is what kind of aspect ratio can a given deposition technique fill, and how does it vary with aspect ratio. So that's just a simple definition, H over W. Slide number 7 I took from the 2003 ITRS, the International Technology Roadmap on Semiconductors. Remember, in the beginning of this course, you read, as a homework set, you read a couple of chapters. Well, I took this from the chapter. They have a whole chapter on interconnect. So this is table 81, and these are predicted interconnect technology requirements in the near term, so to speak, near term being going up to the year 2009, for microprocessor units. If you're talking about DRAM or other types of devices, the requirements are a little bit different, but this is specifically for microprocessors. And we've seen these type of charts before. Let's just go through it here. The columns are the years, so 2004, where we are right now. Remember, this was written a little over a year ago or so, so this is a prediction going up to 2009. And each row tells us some kind of a characteristic. In this case, for interconnect, I have pointed out with the arrows a couple of key characteristics. Let's look at the number of metal levels. In 2004, that was expected on average for a microprocessor is 10 levels of circuit wiring of metal. So that's quite a bit, and you notice that number is increasing over time as we go through 2007. Going 5 and 7 is 11 metal layers, and then going up to 12, and it's going to continue on beyond that. So we're getting higher and higher numbers of metal levels. That's one, which means we're going to have more deposition steps, basically. Another characteristic that is quoted here is metal 1. The metal layers are numbered, by the way, from 1 up to N. So in 2004, if you had 10 layers, they'd be numbered 1 to 10. So metal 1 is the first metal layer, and you're being told here what the aspect ratio is. They use an A/R in the ITRS roadmap. We just define the aspect ratio as being the height to the width for the metal line for copper, and its aspect ratio is somewhere around 1.7. And you see the aspect ratio is increasing over time. And in fact, I didn't show it here, but if you go to the year 2010 and beyond, it goes up to 2, a little over 2. So the aspect ratio, we need to make that an increasing number. And then look at the interlevel metal insulator dielectric constant, the very bottom row of this chart. I actually truncated the chart. There was a whole bunch of rows in the middle, and you can see right here where this little discontinuity, I took it out. If you want to see the full chart, you can go to the website. So look at the dielectric constant. The bulk dielectric constant of the insulator that's going to between each layer of metals is actually going down. Here it is supposedly in 2003, it was around 3. And you notice we get into the yellow region, which means solutions, people have some idea what the solutions are, but they're not ready for manufacturing. People want to go to less than 2.7 dielectric constant. And in the year 2007, they're looking at, would like dielectric constants less than 2.4. And that's part of the red region, which means nobody knows exactly how to do that. So just the opposite of the gate insulator. Remember, in the gate insulator, I was trying to get higher capacitance between the gate and the substrate so I could get better charge control. So in the gate insulator, that dielectric constant, we want to go up. For in the interconnect, we want the dielectric constant to go down. We want it to be lower. And these are the so-called low K dielectrics that are used in the back end. And the reason we want that is just simply, if I have a big stack here, if I'm going back a couple of view graphs here to, say, page number 2, I'm only showing a couple layers. But between this metal layer and this metal layer, I'd like to have a minimum capacitance between the different lines because capacitance leads to RC time delay in the circuit. And in fact, the RC delays, the interconnect delays, are very rapidly approaching the delays associated with the devices. So making the devices faster doesn't do you a whole lot of good if you're interconnect limited. So there's a trend to get new dielectrics in here, all these shading here in blue, to come up with new materials that have lower and lower dielectric constants. Just the opposite of what we want to do with the gate insulator here. We want to make a higher and higher one. So we're going to find new materials coming all the time. So let me skip back to that on slide 7. And again, if you want to see more of this, you just go to the ITRS, and you've been there before, and you just pick the chapter on interconnect. So besides interconnect, though, I don't want to give you the idea that thin films are only used in the back end. They're actually used in front end, and that's what I'm going to emphasize in this course. So I took the diagram I just showed you, and I chopped off the back end to mean what we're talking about, sort of front end. And there are maybe 3 different types of critical thin films that we're going to emphasize, because this is a course on front end processing. So we're going to emphasize the deposition of silicon, either single crystal by epitaxy or polycrystalline by LPCVD. And here's the polygate. Silicon dioxide, which is also called LPCVD oxide, low pressure chemical vapor deposition, or low temperature oxide, and silicon nitride, which I've shown here in green. The spacers are often made of nitride these days, or combinations of nitride and LTO. So that's what we'll emphasize in this class. All the rest above this, which I've erased, if you take 6.773, that hasn't been offered recently because Professor Reif is department head of EECS, so he's been kind of busy. But that course deals with all the types of thin films that are kind of above here. I'll talk a little bit about deposition of metals and things like that, but we won't emphasize it as much as that class does. Okay, so let's go on to slide number 9, and we'll just talk a little bit historically about how some of these films are deposited. And the films we're going to emphasize initially today will be deposition of silicon, either polycrystalline or epitaxially. So there's really 2 main types of methods that are used in CMOS, and you'll hear about them. And one thing I want to apologize for right up the bat is in thin films, one of the things I really dislike is the number of acronyms is really kind of ridiculous. And you'll see that as we go through just this first bullet here, number 1. So the first type of deposition method, and very common, is called chemical vapor deposition. And it is just like the name sounds. You have a vapor of different gases, and you deposit from the vapor phase a film on the wafer. And there are different types. People call atmospheric pressure CVD, and that's abbreviated APCVD. Low pressure CVD, which we'll talk about, abbreviated LPCVD. Now we get a little crazy. There's also plasma enhanced types of CVD, so PECVD, where we use not only thermal energy, but we use plasma energy to break up the constituents and cause the deposition. And there's also high density plasma CVD, or HDP CVD. So it goes on, the number of acronyms that are all associated with CVD. PVD, not so many acronyms, but this stands for the second major method is called physical vapor deposition. This is just as distinguished from chemical. It's primarily a physical process, so there's not as much chemistry involved. And the physical processes that people use, you may be familiar with, is thermal evaporation, which we'll talk about, and sputtering. These are primarily physical, have less chemical, less chemistry associated with them. So let's talk about CVD here first. This is a very old-fashioned sort of classic diagram of an example of an atmospheric cold wall or cool wall system that might have been used for a number of years to grow epitaxial silicon. And I put here in quotations old-fashioned because it's pretty far from what a lot modern epitaxial reactors look like today. And I have some examples of modern reactors in the next few slides, but just to give you an idea. The basic idea was this. You had a series of different gas lines. So here is, for example, hydrogen with diborane or phosphine. These could be used for dopants, for boron and phosphorus doping. You had carrier gases like argon and hydrogen. Hydrogen chloride could be used to etch deposits off the quartz. And here's a liquid source for silicon tetrachloride, SiCl4. Maybe hydrogen was bubbled through that and transported that vapor into the chamber. The silicon wafers typically used to sit on a big block of graphite. And the graphite was heated not by a nichrome heater, but it was heated by induction heating. So there were RF coils. And this is why it's called cold wall, because these RF coils, the RF energy is not absorbed by the quartz, just by the graphite. So just the graphite gets hot here. And the hot graphite then heats the wafers. The chemical vapor passes over, and there's decomposition on the surface, as we'll talk about, and you grow the epitaxial silicon. It's a relatively old-fashioned atmospheric reactor. Let's go on to slide number 10. Now, This is an example of something that you will find. That old epi reactor you probably won't find in too many fabs today, maybe a few of the old bipolar fabs, but this is a reactor that you will find in most fabs, something very much like it. It's called low pressure hot wall system, or LPCVD, and it's used pretty much every day now for the deposition of polycrystalline silicon that is used to form the gate, or for amorphous silicon. Or even silicon dioxide, this type of setup. And what it is it's a regular furnace that is resistively heated, so it's a hot wall system. So the entire quartz tube comes up to the temperature of deposition. Could be 600, anywhere from 400 to 700, something in that range. So everything is hot. And you notice what's very different from the previous diagram. I have some kind of a quartz holder here, and the wafers are standing up. They're not sitting flat, and there's a lot of wafers in here. Could be 25, could be 100, but they're stacked very, very close to each other. And so you can do batch processing, lots of wafers at once. And the whole reason you can do this, and we'll talk about that, is because it turns out the mean free path is quite long when the pressure is low, so the gas can get effectively, the reactants can be transported in between the wafers very, very efficiently. So there's no need to spread them out over a large susceptor, as we had to do in the case of an atmospheric process like this, where we can only get 2 or 3 wafers in at a time. In this low pressure case, you can put in quite a few wafers. And the pressure is kept low in this case by a vacuum pump. So the quartz tube has an opening in the front, which is sealed by an O-ring seal and a stainless steel plate. So that closes the quartz, and you can suck on it with this pump and pull a vacuum. And you have a couple of source gases that with mass flow controllers that control the flow of whatever it is you're using. Could be silane, could be dichlor, whatever. Yeah.
When the ESP bot is gone,
we're going to talk about that. But basically, if the mean free path is sufficiently long, what it means is before the atom can go, or the molecule can go a long distance before it hits a wafer and would stick. The mean free path is very short, and I were to put it in a reactor like this, you'd get deposition all on the tips of the wafers, right at these edges, but it wouldn't get down in between, because the mean free path tells you how often is it that you have a collision. If that mean free path is very, very short, basically, the chance of you having a collision with a wafer is quite high, and you'll tend to react. It's a collision of particles, right? But it also relates to the interaction of those particles with whatever you have in the reactor with the geometry.
it means we want these long, to have like more helium off before.
Well, it's not. This is a chemical process now. Again, when we kind of go through this process, it may become a little obvious. It's not evaporation. You still have the gas flowing and getting in between. So it's still a gas phase type of process. We're not evaporating onto it. So the gas can still flow here in between each of these wafers, and the pressure is low enough that the reactants can get in between, and you can get nice uniform deposition. That's not the case if you do at atmospheric pressure, where you need to have the wafers well separated because you develop boundary layer effects and things like that. Okay, hopefully that'll become a little more obvious as we go on for the rest of this lecture and the next. Okay, what else about this reactor you should know? Remember, it's a hot wall. That's the problem with that, is you get deposition of whatever you're depositing on the wafers also deposits on the walls. That can be give you particulate problems, because you can eventually develop so much silicon deposit on the walls, it'll start to flake, and then you get particles. So LPCVD is notorious for having particulate issues. So that's kind of a basic characteristics of LPCVD reactor. Let's give an example of 2 types of deposition. Here's on slide number 11. The first example was epitaxial silicon, single crystal growth. And I showed you a picture of a cold wall atmospheric pressure system. This particular equation number 1, is again a little bit old-fashioned, using silicon tetrachloride, and it reacts at high temperature and can be decomposed into silicon solid plus HCl gas, which has evolved. You can also, more commonly today, rather than silicon tet, people typically use silane, SiH4. Again, in the gas phase, at high temperature, it can react form solid silicon and evolve off hydrogen. So this might be for epitaxial growth. The second example here, equation number 3, shows the deposition of amorphous silicon dioxide. So this is that famous LTO that we've been talking about, low temperature oxide, that is deposited very commonly in a hot-walled, low-pressure system, just like what I just showed on page 10. This is exactly a low-pressure CVD oxide or LTO furnace. And the way LTO is made is typically with silane, a gaseous silane combined with oxygen, usually in the temperature range of 400 to 500, something like that. Decomposes on the wafer surface. Both of these decompose, and they react to form SiO2 in the solid phase and evolve hydrogen. And notice, because you are putting in silane, you don't have to consume any silicon on the wafer. So that's the advantage. If you need to put down a film and there's no silicon exposed, then you use this LPCVD process to get put down an oxide. Okay, there's a couple of examples. So let's look at this process now on slide number 12 a little bit more carefully. And here maybe we'll see how the pressure comes to play in all this. Slide number 12 talks about atmospheric pressure, or CVD. And what it is schematically, this is the top wall of your reactor. Could be quartz. Here's the bottom wall. Here's a graphite susceptor, which is hot, and there's a wafer sitting on it. And there's a gas stream up here above. Some distance the gas is flowing at a reasonably high velocity. And steps 1 through 7 here are the different steps that people have identified as being involved in chemical vapor deposition. So notice how it's not evaporation. So the first step, we take the reactants that have to be transported from the main gas stream into the deposition region. So they're coming into the reactor over here on the left. They have to get over near the wafer. Okay, that's obvious. It's not usually rate limiting in any way. Step number 2 is the transport from the main gas stream through what's called a boundary layer to the wafer surface. Now, a boundary layer exists whenever you have a static surface and a gas or some fluid flowing above it. And the boundary layer is a layer in which the velocity of the particles actually goes from the velocity it is in the center of the tube down to 0, because right at the wafer surface, the velocity is 0. So you have to somehow get through this stagnant layer. And so transport through the boundary layer is one of the critical processes, and it will be rate limiting in certain types of reactors. Then there are 3 surface processes here. You could lump them all together if you want and just call them surface processes, but they are called out individually here. Number 3 is the adsorption of the reactant onto the wafer surface. 4 is the surface reaction itself, including a chemical decomposition, like what I just showed you, a reaction. If we go back to slide 11, this is what I mean by that step. So it's the actual decomposition of the gas on the surface to crack the gas or decompose it. Could also be surface migration involved in the surface in step 4, or attachment to kinks and ledges. So there are a number of surface processes that happen. And then step number 5 is desorption of the byproducts. And then we have to transport the byproducts through the boundary layer. And then finally transport of that out of the reactor, out of the deposition zone. And I've highlighted here in red steps 2 through 5 because they're most important in determining the growth rate. In fact, the 2 rate limiting steps tend to be step 2, which is transport the reactants through the boundary layer, through the which is usually typically a diffusion type of process, and a reaction process. The second rate limiting step is the surface processes themselves, the chemical reactions usually. Okay, so let's go on to slide 13 and talk about a way to quantitatively and come up with a very simple quantitative model. Now I've turned everything by 90 degrees on you because that's what was done in the text. I took this from your text. So now be a little more careful here. The silicon wafer is now sitting vertically. It doesn't really matter if it's horizontal or vertical. You just have to tilt your head if you want from the last picture. And the gas here, so the gas is flowing vertically. So the gas is going up here the way the laser pointer is. It's flowing by, and it has some concentration here in the main gas stream. And this region that's labeled from here to here by these 2 arrows from the silicon surface to this point here is called the boundary layer. So that's the stagnant layer where the gas velocity in the stream direction is actually going down. Eventually it reaches 0. So within the boundary layer, we typically have a gradient of the concentration of the silane or whatever it is, the concentration of the reactant. In the gas stream, it's called C sub G here. When you reach the surface of the silicon, at the very surface, there's a concentration of that species called C sub S at the surface. And these two F's here, this flux F1 is a diffusion flux, so that's the flux of the reactant species to the wafer, and it's mass transfer. It's called a mass transport or mass transfer flux. And on the previous page, it represented step number 2. So that's this flux F1. Flux F2 is the actual reactant consumed by the surface reaction. So that's the surface reaction rate or surface reaction flux. And that's what I meant by steps 3 to 5 on the previous page. So F2 referred to these surface reactions. So we have these two fluxes. We've got to get through the boundary layer by diffusion. We've got to react at the surface by some chemical reaction. And so we're just going to write down simple equations for flux 1. Transport through a boundary layer, we're going to say that flux, the number of particles going through per square centimeter per unit time, is going to be just proportional to the concentration gradient, Cg minus Cs. And the proportionality constant we're going to call Hg, which is the mass transfer coefficient, and typically have units of length per unit time or centimeters per second. So that's the first flux. That's just transport through the boundary layer. Flux number 2 is the reaction at the surface, and this is a chemical reaction, so we typically write that with its chemical constant, K sub S, some surface reaction rate in centimeters per second, times the concentration of the species at the surface. So again, this is a little cartoon of what we just saw. So in steady state, we're going to let the fluxes through the boundary layer and at the surface be equal. F1 equals F2. So we just equate equations 4 and 5, which we just had. That's pretty simple. We can solve then for C sub S, the concentration at the surface, in terms of C sub G, the concentration in the gas. And we get it's Cg divided by 1 plus K sub S over Hg. Now, we just need to define the growth rate of the film. So the growth rate of the film is this flux F, which we now know. We can write F as K sub S times C sub S, and I just solved for C sub S in equation 7. So the velocity of the growth rate of the film is a velocity V. It's just the flux divided by N, where N is the number of atoms per cubic centimeter. You can just do this dimensionally. The velocity, the flux has units of number of atoms per square centimeter per time. And this is number of atoms per cubic centimeter. So I end up with a velocity of centimeters per second, or centimeters per unit time. So we just divide this flux by the density. In silicon, for example, the density is 5 × 10^22. Multiplying this out, what we get is this quantity K sub S Hg divided by K sub S plus Hg. That times the concentration in the gas phase of the reactants divided by the density. This kind of makes sense if you look at it, or you can look at it here in terms of this quantity Y, where Y is the mole fraction of the incorporating species. So it's the partial pressure of silane, for example, divided by the total pressure of the gas. And it kind of makes sense. As you might imagine, the velocity of growth, or the growth rate, depends on the concentration of the species in the gas phase. That's not too surprising. And therefore it depends on the mole fraction, the partial pressure of the silane divided by the total pressure. So that's a very simple model. And the important thing is now to look at the dependency on K sub S and Hg, and what their temperature dependencies are. So let's go on to slide 15 and look at that. So this is equation 8. I just repeated exactly that same equation we just saw for the deposition rate. And you notice because of the way these add here, the deposition rate is going to be determined by the smaller of the two, of K sub S or Hg. So let's say K sub S is very small. Then I can ignore it here and forget about it in the denominator. Then the Hg's go out. And then in that case, if K sub S is very small, the velocity just depends on, now that I'm doing this case, then just depends on Hg times this concentration. Let's see, if K sub S is much, much less than Hg, then I can ignore it here. The Hg's go out. Oh, and I end up, it's the rate limiting step, and you end up being proportional to K sub S. So in that case, we have what's called the surface reaction case. So this would be a case where the mass transfer through the boundary layer is very fast. You want to think about that, or you could call it in a case where the surface reaction is very, very slow. And so the growth rate in this case is directly proportional to the reaction rate. The important thing about K sub S is to notice is that it's exponentially dependent on temperature. So in this regime, we expect to see the growth rate exponentially proportional or exponentially dependent on temperature. On the other hand, if K sub S is very fast, if the reaction goes very fast compared to the mass transport, or the mass transport here is slow, Hg is small, then we have the mass transfer or gas phase diffusion control case. So here the velocity depends on Hg, which it turns out diffusion through the gas is not a very unlike a reaction at the surface, is not very temperature sensitive. So we expect in this regime to have a very weak temperature dependence. So we can immediately see these two different regimes happening depending on the relative ratio of K sub S to Hg, and therefore depending on the relative temperature. So if we go to slide 16, what people find experimentally, what these rate constants look like. K sub S actually goes like a constant, some number, K naught, whatever it happens to be, times e to the minus EA over KT. So the surface reaction rate has a certain temperature dependence, it's exponential, and it has an activation energy of EA. So if I were to plot that on the growth velocity or the growth rate on a log scale versus 1 over T, what the K sub S term is just going to be a straight line, right? Because it's just, I'm taking the log of an exponential, and therefore I just get a straight line. It's directly proportional to 1 over T. So down in this region here, the slope is directly proportional to the activation energy. Now what happens is as I change the temperature here, and I go to higher and higher temperature, so higher temperature means going to the left, right? Going to lower 1 over T. At some point, what we see is we become rate limited by the surface reaction rate, by the mass transport rather. The surface reaction is happening so fast at this point that its rate overtakes that, and the growth rate becomes limited by transport through the boundary layer. And that transport through the boundary layer is pretty much a constant. It doesn't depend much on temperature. It depends on pressure and the design of the reactor. So in this regime, we expect it to be relatively temperature insensitive. And of course, the net growth rate is neither one of these dashed lines. It's the solid line, which is the combination of the two, where we combine them just like we did here, according to this equation. Equation 8 tells you exactly how to add them up. For example, if you are growing single crystal silicon, typically the activation energy, just to give you a rough idea, it's typically in the range of 1.6 to 2 eV. So that's what the slope down here will be. And again, Hg is relatively constant as a function of temperature. So as an example, let's go to slide number 17, which illustrates some data I took out of your textbook on silicon epitaxial growth. And this is all at atmospheric pressure, so the data is a little bit older. But what you see here is growth rate, and the units are microns per minute. And again, this is a logarithmic scale versus 1 over T, or actually 1,000 over T. So this is a typical Arrhenius type plot. If you want to read the temperature, you can conveniently read the temperature right off here, going from, say, 600 all the way up to 1,200. And there are a couple different curves here. So here's the curve for silicon tetrachloride. Silicon tet doesn't react very well at low temperatures, so its growth rate is relatively slow compared to trichlorosilane, dichlorosilane, which is SiH2Cl2, that's dichlorosilane, very commonly used today, or silane. Silane's the most reactive of all these, and so at any given temperature it has a higher growth rate. You can see that. But look at the shapes of the curves. It's very similar to that previous model, not exact, but you see for any given reactant, let's say silane, we have a region where the growth rate on an Arrhenius plot is a straight line, so it's exponentially activated. It's limited here by surface reaction, very sensitive to the temperature, and then you finally get up to a high enough temperature and it starts to roll off. It never is completely constant, but it reaches a point where the temperature dependence is very small at high temperatures. And so in this we call this high temperature regime the mass transport limited So you're talking about diffusion through the boundary layer, and down here where it's clearly exponential, the surface reaction rate limited. So in old-fashioned silicon epi, people used to do deposition at very high temperatures to get high crystal quality. So in the old days, people typically grew at 1100 or 1150. So they were almost always growing with these reactants in the mass transport limited regime. So they were almost always HG controlled. So the old-fashioned reactors had to have the horizontal reactor configuration because mass transport through the boundary layer depends on exactly how the reactor is designed. Modern epitaxy often operates, however, if people are growing silicon germanium and other materials need to be grown at lower temperatures like 800 or so, or 700, often operates in this regime now, these days, where you're in the exponential regime. So where controlling the temperature becomes extremely important because that, in order to get good growth rate control. Yeah.
We will and go on with
the question is on slide 17 is about what happened to the silane in the nitrogen ambient. Why, you see this dashed line, you notice the growth rate for silicon using a nitrogen ambient instead of a hydrogen. These are all grown in hydrogen, which is typically used for higher purity. The growth rate pops way up at the same temperature. And the reason for that is if you go back and look at a couple of slides, let's see if I can find the chemical decomposition. On slide number 11, if you look at equation number 2 for the chemical decomposition of silane, silane in the gas forming silicon, solid silicon, it evolves. The reaction when you grow epitaxial silicon with silane, it evolves hydrogen. So hydrogen has to come off. Now this is a chemical reaction, so you know you can push it to the left. You can tend to slow down this reaction if I put a lot of hydrogen in the ambient. So using a hydrogen carrier gas tends to push this to the left and tends to cause this surface reaction to be less probable, and the reaction rate goes down. But if you, instead of using hydrogen as the carrier gas, if you use an more inert gas like nitrogen, you won't have that pushing to the left effect, and so the growth rate goes up.
And we smell out. And it's not squished in this 3D. Why did it buy the players?
Well, let's see. In the transport limited regime, you're still going to have, I mean, you still have, well, there is a little bit, yeah. Well, in the transport limit regime, it looks like we never really get there with this dashed data. They sort of petered out a little bit. So it's almost getting to the transport limit regime. But the problem is the surface reaction rate is so fast now, it's hard to see the transport limited regime. But it looks like they're converging. It looks like the two are converging. Because at that point, the reaction rate really isn't what's controlling it. It's transport through the boundary layer. So the question is, well, what's the difference in transport between a boundary layer and a nitrogen versus a hydrogen? There's probably some small differences there. Okay, so let's go on to slide number 18. We were just saying how transport through the boundary layer is important when you're in the high temperature regime or the mass transport limited regime, and therefore it turns out that the reactor geometry in the high temperature regime is very important, how you build the reactor. And I've taken this on slide 18 here. I've taken this picture from your textbook, figure 9.9. And what it's showing is the velocities in the boundary layer. The velocities are represented by these little arrows along the susceptor and going from left to right. So the gas is coming in at the left, flowing over the wafers and the susceptor, and going out the right. And according to some gas flow laws, Newton's second law, the boundary layer, the thickness of the stagnant layer, which is represented by the height of this layer above the wafer surface, this delta sub S, you see this height or the thickness of the stagnant layer is actually increasing. So, and this boundary, this dark region represents the thickness of the boundary layer. And you notice beyond the boundary layer, above it, the gas velocity has reached the same as the velocity as it is in the center of the tube. It's only within the boundary layer that the velocity is decreasing. So these arrows, their lengths are decreasing. So as you flow gas through a pipe against the surface, the boundary layer thickness is actually increasing. Now, this process of diffusion through the boundary layer, this quantity, the Hg, the mass transport coefficient, it has to do with diffusion through that delta sub S, that thickness, delta sub S. So people write in a crude way that Hg is equal to some diffusion coefficient in the gas phase divided by the thickness, delta S. But see, delta S is not constant as the gas flows along the surface. So people try to manipulate things to try to make delta S more constant across the reactor surface. Otherwise, what will happen is the growth rate here will be much higher on the first wafer than it would be on the last wafer in the reactor. So people try to compensate for that. A certain type of reactor geometry is usually required, therefore, to get uniform deposition across a number of different silicon wafers if you're working in this mass transport limited regime. A typical trick is to tilt the susceptor. So take the susceptor and tilt it. And how does it? Well, this increases the gas velocity, which keeps delta sub S constant. So as I'm going, the gas velocity at this point, so imagine I'm flowing the same volume of gas, a certain number of liters per minute, through this cross section from here to here. The gas velocity has some value. Now if I go here, the cross section has decreased. So the velocity, so again, I'm getting the same volume, number of liters per minute. So the velocity of the gas in a smaller cross section tube must therefore go up. So V is increasing now from left to right, which was not the case when the susceptor is flat. When the susceptor is flat, the velocity here is called U, and the center is the same from left to right. And so what we're doing is to compensate for this, to make the boundary layer thickness perfectly flat, we tilt the susceptor to up that velocity in the center of the tube. But there's another issue though with non-uniformity. Not just so that you can take care of the boundary layer effect by designing your reactor appropriately. The source gases themselves can become depleted along the length of the susceptor. So you maybe have less silane back here than you have here because a lot of it may have reacted. What people sometimes do then is they sometimes introduce a temperature gradient along the flow direction. So you might make the temperature here just a little bit hotter than it is here to try to compensate for that and try to get uniform thickness on the first wafer and the fifth wafer in such a type of reactor. So if we go on to slide 20, now there are some implications of this, what we know about how CVD works now based on our simple model of surface reaction rate and mass transport rate on the reactor design. If we look at a horizontal reactor, and this is supposed to represent the tilted susceptor, if the deposition occurs in the range of say 1 torr to 760 torr, relatively high pressures and relatively high temperatures, then the mass transport to the wafer surface is the most important thing. It's more important than the surface reaction rate. And that places some severe restrictions on the geometry of the reactor and on the gas flows and how the wafers are stacked. So typically in that case, atmospheric pressure or relatively high pressure, epi, you'll see it in reactors that only have a few wafers in them, and the geometry of the reactor and how you stack them is really critical. So when the deposition occurs primarily at low temperatures and low pressures, so we're in the millitorr regime or hundreds of millitorr, we're surface reaction rate controlled. So it's very sensitive to the temperature, but it's not so sensitive to transport through the gas boundary layer. And the mean free path is long enough that the mean free path issues don't come into effect. In this case, for this type of process then, where we're working in the 100 millitorr range, and the temperature is low enough that we're surface reaction rate limited, we can stack the wafers together relatively closely. So you see in an LPCVD process, which LPCVD usually works at around a few hundred millitorr, you can stack a lot of wafers close to each other. You still have to worry about gas depletion in LPCVD. So what people do is when assuming the gases are coming in here and going out, say they're going from left to right, people will again tilt the profile of the temperature in the furnace. So typical LPCVD system will have 3 zones, a front zone, a middle zone, and a back zone. And the back zone is usually kept a little bit hotter than the middle or the front zone because, again, the silane or whatever you're depositing tends to get depleted. So you make up for that by increasing the surface reaction rate a little bit, by increasing the temperature. So you hope you can get the same thickness on the first wafer as you got on the 50th wafer or whatever. And that needs to be done somewhat empirically. So on slide 21, I'm showing some classical geometries for epitaxial reactors. I took this from Simon Z's book. He has a VLSI technology book that he edited. There's a whole chapter there on epitaxy if you want to see more details on it. These are some schematics of some of the common old-fashioned epi reactors. There was something called a radiant barrel. The barrel reactor was shaped like a barrel. The gas would come in at the top and exit out the bottom. And there would be sort of cylindrically shaped, but with flat surfaces, sort of susceptor. And you see each one of these circles is supposed to represent a wafer sitting on the susceptor. So you could get a fair number of wafers in it at one time. And notice the gas, they were trying to do the equivalent of susceptor tilting by decreasing the cross-section through which the gas flows from the top, the wafer at the top, to the bottom where the gas exits. There are also vertical reactor geometries where the gas would come in and go out like this, and the horizontal we've already talked about. So all of these were in the cases where are typically multi-wafer tools, where you grow anywhere from 5 to 20 wafers in a typical epi, in an epi batch. It's the more classical or maybe old-fashioned type of reactor. Slide 22 is a more modern epitaxial system that you will see in fabs today, particularly fabs that are growing silicon germanium for bipolar transistors, or even silicon germanium now used in CMOS, in source drain regions of CMOS. Intel has a commercial process. In both of those cases, bipolar or CMOS, people have moved away from the old-fashioned to the more modern single wafer epitaxial silicon in order to get the kind of uniformity they would need over a single wafer. As the wafer diameter is increased, people are now at 12-inch wafers. The reactor would become gigantic if you had 12-inch wafers, along a system. It's much more efficient to do a single wafer in a chamber at a time and get the throughput high enough that you can do that. So this is an example of a system that's manufactured by Applied Materials. We actually have one here at MIT. This is sort of an overall view of the system. What it has is 2 different load locks. So the load locks are designed so you can open them up to air without putting air into the reactor itself. So you can keep the reactor very clean. So you can open this door, put the wafer cassette in and close it and pump it down, get most of the air out, so you don't just open up the whole reactor and get all the air in and contaminate it. And there's a couple different load locks. There's a chamber in the center called the transfer chamber, which has a robot in it. And here's a picture of the robot. It has 2 little arms, looks like a frog arm. The robot will come out, grab a wafer from the cassette, put it into the transfer chamber, and close this door again, so you don't allow any air to get in. And then it'll take the wafer according to how it's programmed and put it in one of these 3 chambers, depending on how you've programmed it. And you can have up to 3 chambers here, growing different materials, silicon or silicon germanium. So they increase the throughput by having 3 chambers instead of having 3 wafers all along the susceptor in a single chamber. Typical growth pressure in this type of equipment is in the 1 to 100 torr range. So it turns out both surface reactions and mass transport are important. Growth temperatures can be anywhere from 400, very low if you're growing some special material. Typically, silicon germanium is grown between 600 and 800, and high temperature silicon can be grown up to 1100 in this type of system. Just taking a little more zoomed in look at this more modern reactor on the slide 23. This is that same picture. The only difference is here we're showing in a single chamber right here, one of the chambers. And this green object is meant to be a wafer that is sitting on a susceptor that's spinning. So the wafer is spun at high velocity, say 30 revolutions per minute, to try to get good uniformity across the wafer. And the gas comes in here through a series of injectors as a plane, flows across the entire wafer. So the inject is over here, and it flows laterally across, and the exit or the exhaust would be over here. And the wafer spinning. So the chamber is designed with both in mind. Both the control of the boundary layer is important, as well as the control of the temperature. There's a lamp bank that sits on top and bottom that tries to uniformly control the temperature from center to edge to get good uniformity of the epi. So that's a more modern single wafer piece of equipment. So let's just go back one more time to think about, on slide 24, the basic example of silicon epi. I just showed the slide before. of the temperature effects, depending on the relative speed of the surface reaction rate and the mass transport through the boundary layer, you'll be in one of these two regimes probably. This curve on the lower right is interesting. It shows the reactant flow or the partial pressure effects. So this is, before I was showing growth rate versus 1 over T. So these are at fixed temperature. Each curve is for a fixed temperature. And I'm showing growth rate versus the percent of the reactant. So this is the percent of dichlorosilane that's in the gas stream, or you could think of it as the dichlorosilane flow. So interesting, if you go here at lower with dichlor in this particular reactor, again, this will be reactor dependent, at 840 degrees, the growth rate is independent of the flow of the dichlorosilane. So it doesn't matter. You can increase the partial pressure by a factor of 2 or 3. You're not upping the growth rate anymore. You have enough there, and you're really limited by instead of the partial pressure, you're limited by the temperature, the rate at which the reaction can occur. So at low enough temperatures, it doesn't do you any good to flow more gas. As you get to higher temperatures here, say at 1,000, you can see that the growth rate is pretty much almost linearly proportional up to a certain flow is proportional to the flow, or the because basically at this point the surface reaction is going faster and faster as you give it more reactants, and at some point it saturates out. So depending on what temperature you're in, increasing the flow may or may not increase your growth rate. So if we go to slide 25, there's another process that we want to talk about. We talked a little bit about design of the reactor for growth rate uniformity and things like that in epitaxial growth, but the uniformity of the layer thickness is really only one aspect, and these days it's pretty well nailed. But another aspect that's just as important is called autodoping during epitaxial growth. And it's sort of unique to epitaxial growth. We don't usually think about it as being an issue in deposition of other types of films. But autodoping, as the name implies, is automatic or unintentional introduction of dopants into the epitaxial growing layer. And there's a couple of different regions it can come from. First, before we look at the reactor at the top, let's just look at this diagram at the bottom of slide 25. And it's a plot of the concentration on a log scale of a dopant as a function of your distance into the epilayer. So if you it's a little bit backwards, but going from 0 to here is your distance into the epi. So the epi is getting thicker from left to right, and everything to the left of 0 is the substrate. So here I'm in the substrate. So what we're doing in autodoping, you can imagine, I might have a substrate that's heavily doped, say for a silicon bipolar process. So I have a substrate that has some concentration at the surface, and some of that dopant is going to make its way into the epilayer as the epilayer grows. And one process say I'm trying to grow a lightly doped epilayer on a heavily doped substrate. One process by which it will get in there, you already know, and that's diffusion. In fact, we know it's going to be a complementary error function type of profile if it's simply up diffusion from the substrate into the epilayer. So that's relatively simple. We know how to solve that. And then we can limit the temperature and all that, and that will help us limit how far this autodoping goes into the epilayer. But there's another process here, which I'm shown by this sort of exponential dependence, exponentially decreasing function that has a certain decay length, and that's called front-side or vertical autodoping. And vertical autodoping refers to the fact not so much up diffusion, but just the fact that as I grow a single layer, if there is a phosphorus atom there on the surface, it tends to want to be up on the surface. So it tends to want to exchange sites instead of being buried with the silicon. And the phosphorus will ride up the surface. Same thing for arsenic. These dopants tend to like to be on a free surface. So as you're growing the crystal, they will ride themselves, not by diffusion, but just by surface exchange at the surface. They'll ride themselves up the epilayer. And it's called vertical autodoping because it happens directly from the buried layer. It just goes vertically straight up. So that surface riding effect is really a function of the nature of the dopant and the temperature to a certain extent. But the nature of the dopant, it turns out the N-type dopants, arsenic, phosphorus in particular, like to be on the free surface. They're very happy being on a free surface. So they float to the surface, and they make it very hard to make a lightly doped epi layer because they tend to autodope. They tend to have a long tail. Boron, on the other hand, doesn't mind being buried in the crystal. So boron doesn't have much autodoping. It does not surface ride very much. So this tail is not a diffusion limited process. It has to do with the affinity of the dopant for the free surface during the growth process. And then there's this final background that you'll see in an epi layer, which is I'm showing here in green, sometimes called backside or lateral autodoping. And what that refers to is you can get, say, if the back of the wafer is heavily doped, when you heat this thing up, you can actually get dopants coming off the back and finding their way onto the front of the wafer. They could be coming off the susceptor. Let's say you just grew a doped epi layer, but the run before this, you're growing doped epi, and you put in some phosphorus. So that phosphorus now can still hang around in the susceptor, and then it can be transported when the susceptor is heated onto the wafer. So it could be from the back of the wafer, it could be from the susceptor, it could be from another wafer that has a heavily doped region on it. So it's lateral because it's coming from somewhere else. And this is very often a function of what you just grew, maybe a memory effect of what was grown in the reactor, and how it's designed, how well the susceptor is sealed and things like that. So when the epitaxial growth process, we don't worry just about growth rate and its uniformity. We have to think carefully about temperature and pressure and the nature of the reactor design to avoid this type of autodoping effect. Slide 26. Let's say a little bit about how epitaxy has evolved in CMOS and bipolar technology, just so you have a view of where it comes from. Originally, in the old days, epi was originally primarily used just to provide a lightly doped layer on top of a heavily doped substrate for either bipolar or CMOS device processing. So epitaxy in the old days, and there is no chalk because we had color chalk last time, so it was simply a way, if you had a heavily doped wafer and you needed a lightly doped layer on top, maybe 10 microns, it was a way to produce that. There really wasn't any other way. And CMOS and bipolar foundries or companies didn't do epi. They bought epi wafers from one or two places in the world, half a dozen places where people grew it. So you would just buy an epi wafer. That's still a very large market, a very large component of epitaxial technology is simply to produce wafers that are heavily doped substrate, and you need a lightly doped layer on top. But actually, in the last 10 or 15 years, the technique really has evolved, and now it's used to do much more than that. People grow very complex doping profiles. They grow layers of different materials. Silicon germanium is grown on silicon, for example. It could be grown selectively. That means in only certain regions of the wafer where there are openings in the oxide. Could be selective epi can be used for the source drains, on top of the source drains to elevate them. It could be used in the active regions of heterojunction bipolar transistors. So epi has gone from being just the type of wafer you buy to the point where manufacturers of silicon chips now, a lot of them have epi reactors in their fabs, and they use them. And they use those reactors to actively grow structures. So as this evolution took place, several things had to happen, and that's why these new single wafer reactors have come out to a certain extent. The cleanliness of the system and the purity of the gases had to be improved. And that's because the epitaxial growth temperatures are going down, and there's a tendency for impurities like oxygen to be incorporated much more readily at low temperatures. So in order to deal with that, as we lower the temperature of growth, we need to have a cleaner reactor. Otherwise, you're going to put a lot of oxygen in your epitaxial layer. Again, and the pre-clean temperatures have also lowered. So the reduction in the growth temperature and reduction in the pre-clean temperature means epi now has a lower thermal budget. It used to be 1150 degrees for an hour. Now people grow silicon germanium layers at 700 for 10 minutes, something like that. So it can be a relatively low thermal budget process now. And that's important because that means you can have epitaxial, you can have other dope structures on the wafer and not have to worry too much about TED or other things going on. But in order to have low temperature growth, you really have to have a clean reactor. So the new paradigms I've already showed you are single wafer tools. There are rapid thermal epitaxy systems, so that just like rapid thermal annealers, but you can grow epi in them. And there's also something that is not used in production very often, but is used in research. It's called molecular beam epitaxy. It is not a manufacturing process generally because the throughput is horrible, but it's very good for research. It's good for growing new types of materials for the first time. And then people figure out how to grow them by CVD, and they go from there. So that evolution that I just explained in words is shown here pictorially on slide 27. In the 1970s, probably before you guys were born, maybe, or you were just being born, I don't know, something like that. No, it's before you're, no, yeah, it's a long time ago. This is what epi was. You have concentration versus depth in a bipolar transistor. The epi was simply formed the collector. You just grew a silicon epi layer. You would buy a wafer with 5 microns of epi on it, and on top of that you would diffuse in or ion implant your base, and then you diffuse in your emitter, and you make an NPN bipolar transistor. And the epi layer was pretty thick, 5 microns. In the 1980s, again, it was silicon epi, and the epi layer was shrunk by a factor of 10. Bipolar transistors, the total thickness was about ½ micron. So in those 10 years, the epi layer thickness had to drop by a factor of 10. People had to learn how to do auto-doping reduction. They had to change the pressure and the temperature to try to reduce this out diffusion and the auto-doping of this N+ buried layer into the active region. And finally, in the 1990s, what people started to do, instead of just growing the collector, people started to grow not only the collector by epi, but the base. Instead of using an ion implanted, look at this, you can see this very broad profile with a retrograde. That's not necessarily what the device designer wanted. That's just what they got when they ion implanted it. In fact, you can grow a very thin, narrow profile with a very abrupt base doping by epitaxial growth. And so epi transformed from just growing the substrate to being able to grow the base layer, either a silicon base, or people then inserted silicon germanium into it, and IBM and others commercialized the silicon germanium, silicon heterojunction bipolar transistor. And that was all based on the development of silicon and silicon germanium epitaxial growth technology. So it's really come from tens of microns now to people grow. Typical base today in a heterojunction bipolar transistor is 400 angstroms. So people are growing 400 angstroms of silicon germanium commercially in production on thousands of transistors on circuits all the time and selling them. So what are the most common gases here on page 28 today for epi? Silane is quite common, and we saw the decomposition reaction before. Dichlorosilane is also popular, has a lower growth rate, but it gives you better selectivity if you're trying to deposit the epi in windows. It's not too unusual to have a wafer where you, in cross-section, where you have oxide like this, and you've patterned the oxide. And you can grow, it turns out, by a process called selective epi. You can grow it in such a way that the epi only grows in the silicon, where the silicon is exposed. So you get epi here, and you get epi growth here, but you get nothing on top of the oxide. So it's automatically sort of self-aligned, and this is called selective epi growth. And to do that, you usually need dichlorosilane. This is the reaction. It's silicon plus H2 plus Cl2 decomposes into another species, and that eventually decomposes on the surface to grow. And it forms HCl, and the HCl is important, it turns out, in etching the silicon off of the oxide, so to keep it so you only deposit in the holes in the selective epi growth. So those are two very commonly used gases. All right, let me just summarize. So far on thin film dep and epi, we have two main types. We said there's chemical vapor deposition, which we talked about today, and physical vapor deposition, which we'll talk about in the next couple lectures. Traditional epi growth uses atmospheric pressure. More modern systems use low pressure methods, typically in the 1 to 100 torr these days. We have a very simple model we developed for atmospheric CVD, and it led to two rate limiting regimes: surface reaction rate, where the growth rate is exponentially dependent on temperature, activation energy of about 1.6 to 2 eV. And then at higher temperatures, you become mass transport limited, and you have very little dependence, very slight dependence on temperature. The mass transport limit regime is good in some ways. It gives a high growth rate. But the bad thing about it is very sensitive to how you design your reactor. So it's a little bit tricky. Reactor geometry has to be well designed. LPCVD in the 100 millitorr range in a hot wall batch reactor is used every day in fabs, particularly to deposit things such as a polysilicon gate, low temperature oxide, and silicon nitride. And we're going to talk about these three types of films and this type of process next time. All right, that's all I have for today's lecture. Just in case you came in late, the clipboard is going around. Make sure today you put down on that clipboard your topic. I really want to have them so I can approve them. Tuesday's a deadline on that. Also, if you didn't pick up any prior homeworks, they're in the back.
Being